Now let's think a little bit more about velocity, the rate at which location changes. Here's our definition. Right, velocity is just the displacement divided by the length of time it took to make that displacement. Actually, the book refers to this as just plain velocity, and then a few sections later goes on to define a different type of velocity. I prefer to call this not just velocity, but it's a specific type of velocity. I should call it average velocity. So I just draw the line over top. The line over top is our usual way of indicating average. That is, in this case, we're watching the moving thing for some length of time, and what we're looking at is really the overall net result of whatever kinds of motion took place in that time. Sort of an average. Another thing to notice here, this is a vector. Remember, a vector is something that has both magnitude and direction. And the only thing that a vector could be equal to is another vector. And to be equal, the two vectors have to have the same size, the same magnitude, the same absolute value, whatever you want to call it, and the same direction. So this is a vector. This thing here on the right-hand side is also a vector because it's the only thing this vector could be equal to. And the direction of this vector must be the same as the direction of this vector. And the only piece here on the right-hand side that has any direction is delta x. So, the moral of the story, the direction of the average velocity vector is the same as the direction of the displacement. Or direction of the displacement is the same as the direction of the average velocity vector. So let's look at a motion diagram and think about both displacements and average velocity vectors. Here's our motion diagram. The motion starts here, and at the end of the first time interval, the object is there. And at the end of the second time interval, the object is there. And at the end of the third and fourth time intervals, the object is there and there. So, if you just draw an arrow that connects consecutive dots, you will have drawn an arrow that correctly symbolizes displacement. Because, remember, a displacement vector always points from the initial location directly toward the final location. And during the first time interval, this was the initial location, and this was the final location. And the magnitude, size, absolute value of a displacement just tells you the length between the starting point and the finishing point. So here's a vector that is as long as the distance between the starting and the finishing point in this diagram. And each of these displacements points from the beginning of that displacement toward the end of that displacement. Here's the displacement during the third time interval. Here's where the object was at the beginning of the third time interval, and here's where it is at the end of the third time interval. But draw that same motion diagram and again draw arrows that connect the dots. Those arrows that connect the dots correctly symbolize not only the displacement during those times, but they also correctly symbolize the average velocity during those times. Why is that? Well, first of all, the direction of displacement is the same as the direction of average velocity, and all these average velocity arrows have the same direction as the corresponding displacements, that is, pointing from the initial to the final location in each time interval. And since in a motion diagram all the time intervals are the same, that is, the time it took to get from here to here is the same as the time it took to get from here to here, and that's the same as the time it took to get from here to here, and that's the same as the time it took to get from here to here, then that means that in this equation, whatever displacement you're talking about, displacement 1 or 2 or 3 or 4, delta t is the same in every case. This number is the same in every case. So if the size, the magnitude, the absolute value of the average velocity vector is going to be different, it can be different only because the size or the magnitude of the displacement is different. Since this delta t is the same amount of time for all 4 of those displacements, then you can imagine that if you put in here a displacement that was 2 times larger, the denominator hasn't changed, so the average velocity is 2 times larger. If you put in a displacement that was only 1/3 as large, this number hasn't changed, so the new average velocity is only 1/3 as large. In other words, the largest displacements will correspond to the largest velocities. The smaller displacements will correspond to the smaller velocities, so that the relative lengths of these average velocity vectors, since they're the same as the relative lengths of the displacement vectors, will correctly show you the relative sizes of the average velocities, the relative magnitudes of the average velocities. That's why in the book very often you'll see a motion diagram with green arrows connecting consecutive dots. Those green arrows represent the average velocity during that particular time interval. Now, we distinguish between velocity, or average velocity as we're thinking about now, and speed, or average speed is what we're really thinking about now. And the rule for average speed is a little different from this. Might look superficially similar, but there's an important difference. I'll leave up here the rule for average velocity vector. Speed, and put the line over top to indicate that we're really talking about average speed in this case, is just the distance traveled divided by the length of time it took to travel that distance. So for example, think about the second hand on a clock. The second hand on a clock, or the tip, the end of the second hand on a clock, sweeps out one complete circle every minute, one complete circle every 60 seconds. So the distance that the tip of the second hand travels in 60 seconds is just equal to the circumference of the clock. And let's say we have a somewhat large wall clock. Hang on here, I've got to fix this. Okay, there we are. A somewhat large wall clock whose circumference we'll say is 0.9 meters, 90 centimeters. 0.90 meters or 90 centimeters. And of course, the tip of the second hand travels that 90 centimeters in 60 seconds. So the speed, of course, average speed, is 0.9 meters divided by 60 seconds. And do the math, and that'll come out to, it's easier to think about these things in scientific notation, or at least it's easier for me. So I write this as 9 times 10 to the minus 1 meters, and this is 6 times 10 to the plus 1 seconds. So 9 times 6 is 1 1/3, and then dealing with the factors of 10, 1.3 times 10 to the minus 2. 1.3 times 10 to the minus 2 meters per second. That's the average speed for the second hand as it moves around the clock. What's the average velocity? It's different. Remember, average velocity is displacement divided by the length of time it took to make that displacement. And displacement is just the final location minus the initial location. And in this case, the second hand makes one circuit around the circle in 60 seconds. 60 seconds is the denominator there. 60 seconds is delta t. But the tip of the second hand makes one complete 360-degree trip around the circle, which means it ends up at the same place where it started. It makes a round trip. The final location is the same as the initial location. And if the final location is the same as the initial location, the net change in location, also known as displacement, is no change. It ends up at the same place where it started. So final minus initial location is 0. So the average velocity is 0. There was speed, that number there, 1.3 times 10 to the minus 2 meters per second. There was an average speed, but there was 0 average velocity. Average velocity, average speed measure two somewhat different things. And when we get to talking about the other kind of velocity and speed, we'll see the same thing. They too will measure somewhat different things.